Hey everyone, and welcome to this explainer. Okay, we've got a lot of ground to cover, so let's just dive right into this. A lot of people hear the words inorganic chemistry and they immediately picture, I don't know, impossibly complex formulas, endless memorization, just absolute chaos. But I want to completely shift how you see this today. Because inorganic chemistry, it really isn't scary at all. It's actually this beautifully logical secret language. It has its own alphabet, its own syntax, and most importantly, a strict yet incredibly simple economy of atoms. So today, we're going to learn exactly how to read that language and balance those chemical books. So here is our quick syllabus for mastering the economy of molecules. We'll hit 1. The economy of atoms. 2. Oxidation rules. 3. Creating perfect couples. 4. IUPAC versus traditional naming. 5. Binary families. And finally, 6. Ternary compounds. Let's get started.
All right, kicking things off with Section 1, the economy of atoms and setting our boundaries.
Before we look at the bank accounts of our atoms, we need to understand the map. You can kind of think of organic chemistry as this one very specific, highly populated neighborhood where carbon is the absolute star of the show. Inorganic chemistry, which is what we are looking at today, is the rest of the periodic table's sprawling metropolis. It includes literally every other element, plus a few carbon exceptions that act more like, inorganic tourists. Things like carbon oxides, cyanides, and carbides. Basically, this is the big, wide world of chemistry. Okay, so the absolutely crucial point is right here, the oxidation number. Seriously, if you take away just one thing from this entire explainer, let it be this. The oxidation number is basically an atom's credit score, or its bank balance in this chemical economy. And electrons? Electrons are the currency. If an atom loses electrons, its balance actually goes up, becoming positive. If it hoards or gains electrons, its balance goes into the negative. This single number tells us immediately if an atom is likely to generously give away its wealth or aggressively take electrons from someone else. Now, think about pure elements for a second. Things like liquid mercury, crystalline iodine, or solid sulfur. These are atoms that only associate with themselves. Because they aren't trading with anyone else, they're basically like people living completely off the grid. They have absolutely no chemical debts and no chemical credits. So their bank balance, their oxidation number, is a perfect, stress-free zero. Moving right along to Section 2, oxidation rules. These are the absolute rules of our atomic economy. When two different atoms form a bond, it is essentially a business transaction. But let's be real, it's almost never an equal partnership. The rule here is super simple. The shared electrons are formally assigned to the most electronegative atom. And electronegativity? That's honestly just a fancy word for bargaining power. The atom with the highest electronegativity acts as the boss of the molecule. It dictates the transaction, hoards the wealth of those shared electrons, and drags its oxidation number down into the negative, while leaving its partner stuck in the positive. Now, in any global economy, you've got fixed exchange rates, right? Constants you can always rely on. Well, in inorganic chemistry, we have two major ones. Hydrogen is like the ultimate generous spender. In almost all its compounds, it gives up its electron, leaving it with an oxidation number of +1. Oxygen, on the other hand, is a total stubborn hoarder. It's highly electronegative and almost always takes 2 electrons, leaving it with a rock-solid bank balance of -2. If you can just remember that hydrogen is a +1 and oxygen is a -2, you can decipher pretty much any chemical transaction.
Okay, Section 3, creating perfect couples, the matchmaking of binary formulas.
A binary compound is just two atoms coming together to perfectly balance their books so their total debt and credit equals 0. And how do we actually do this? Well, it's this incredibly simple 4-step matchmaking process. First, write the symbols, putting the generous, least electronegative one first. Second, write their bank balances, their oxidation numbers, right on top. Third, you literally just cross those numbers diagonally down to become the subscript for the other atom, dropping the plus or minus sign. And fourth, if those bottom numbers can be mathematically simplified, you just reduce them.
You've got to look at how beautifully this works in practice. So, say we have sulfur with a high positive balance of +6 and oxygen with its standard -2. We cross them over diagonally. The 2 from oxygen goes to sulfur. The 6 from sulfur goes to oxygen. So temporarily, we get S2O6. But wait, 2 and 6 are multiples. We can simplify that just like a fraction in elementary math class. Divide by 2, and we get SO3. Boom. The books are perfectly balanced to 0. All right, Section 4, IUPAC versus traditional naming conventions. Because now that we have our couples, we need to know what to call them.
So this chemical language actually has two distinct dialects. Think of the IUPAC name as the strict, official passport name. It states exactly, literally what is there. For example, Fe2S3 is diiron trisulfide. 2 irons, 3 sulfurs. No ambiguity whatsoever. The traditional name, however, is a bit more like a vintage family nickname. It looks at the metal's bank account. Iron, for instance, can have different oxidation states. If it's using its smaller balance, it gets the suffix "us", like ferrous sulfide. If it's using its older, larger balance, it gets the suffix "ic", like ferric sulfide. It's definitely a bit old-fashioned, but you still hear it all the time in labs and, on the back of ingredient labels.
And if we look a little closer at that official IUPAC syntax, you'll see it actually reads backward compared to how we write the formula. Take LiCl. You read it from right to left, kind of like translating a foreign sentence. You start with the most electronegative element on the right, chlorine, and add the suffix "ide", making it chloride. Then you just say of the first element, lithium, lithium chloride. It's a really straightforward logical translation once you get the hang of it.
Moving to Section 5, Families of Binary Compounds. Let's look at the different types of couples. We can actually categorize our couples based on who is partnering with whom. We've got binary salts, which are your classic metal and non-metal partnerships. We have oxides, where oxygen is acting with its standard -2 valence. But what's really fascinating here is how the currency can occasionally shift. Look at hydrides. Suddenly, our normally generous hydrogen is acting as a boss, taking an electron and holding a -1 valence. Or peroxides, where 2 oxygen atoms bond directly to each other, forcing them to share the wealth and hold this unusual -1 valence, instead of their standard -2. It's the exact same economy, just with a few specialized tax brackets.
And that brings us to Section 6, ternary compounds, or what I like to call the 3-ingredient recipes.
So here is the big question. What actually happens when our chemical couples invite a third wheel? I mean, imagine the shift in the economy when a simple 2-person partnership suddenly becomes a 3-piece band. The accounting definitely gets a little more complex, sure, but the ultimate goal remains exactly the same. You have to balance the total ledger to 0.
When we add a third element, we enter the world of ternary compounds. You can think of these as specific, rigid recipes made of exactly 3 ingredients. The 3 main types you're going to encounter are hydroxides, oxyacids, and oxygenated salts. Let's briefly look at the rules for the first 2 because they perfectly illustrate how our atomic economy scales up.
So the absolutely crucial point about hydroxides is that the metal atom dictates the entire party. A hydroxide is just a metal paired with an OH group, which is an oxygen and a hydrogen acting together as a single unit with a -1 charge. The rule here is incredibly elegant. The metal's positive credit score strictly dictates exactly how many of these -1 OH guests it can invite. So if calcium has a +2 balance, it needs exactly 2 OH guests to zero out its account. Make sense?
Now, oxyacids are even more fascinating. Think of them as just taking a non-metal oxide and adding a splash of water. When you add H2O, you get an acid. But what makes them really special in our chemical economy is that they can act like banks, releasing funds into the wild. They can easily release their positively charged hydrogen ions, those H+ ions, into water. And when they lose that positive charge, the remaining molecule, the oxyanion, is left with a negative debt, equal exactly to whatever it just gave away. It's perfect accounting. And honestly, this brings us full circle. Inorganic chemistry is never about blind memorization. It is purely about understanding these financial transactions and the grammar rules of atoms. Because once you know who wants to give electrons, who wants to take them, and how they balance their checkbooks to 0, well, you aren't just memorizing formulas anymore. You are actually reading the invisible architecture of the universe. So I want to leave you with this somewhat provocative thought. Every single object you touch, the air you're breathing right now, the screen you are currently looking at, it's all the result of trillions of microscopic, highly regulated financial transactions happening every single second. Atoms constantly negotiating, crossing over, and balancing their checkbooks to 0. Now that you know the rules of their economy, what do you see when you look at the world around you? Keep that in mind and keep decoding. Thanks so much for joining me on this explainer.